Hello. Let me see. This should work. Yeah. Okay, good. So yes, it's a rehearsal today. Sorry, I'm still trying to finish making this drink, this whatever 面茶. Anyways, okay. So first of all, if you found this, found this VOD or whatever through the YouTube search, then because you are here for like the scientific or like tech content or whatever, just know that this is a rehearsal. So this is going to be incredibly undercooked and scuffed. But good news for you is that I think the actual, what is it called? The actual talk, because this is a rehearsal, so of course there is gonna be a real deal. And the real deal is also going to be recorded, and it is also going to be uploaded on YouTube as a separate video. So I will be linking the actual video in the description below. So, um, yeah, so check the description, or I guess check the, I don't know, description or comment. Yeah, I will link it somewhere. So basically, if you are here for the actual scientific content, maybe look for that because, like I was saying, this is a rehearsal. So this one will be incredibly scuffed. Sorry if I'm just looking not at the camera right now because I am trying to stir my thing. Yes. Um, yeah. So with let's say no, if you are just here because you like to watch me, then well, you are at the right place. Thank you very much. I like you too. Um, okay, so the other thing is okay, yeah. So face cam because as I think I mentioned it like once or twice before, but I mean the ideal scenario is that I just be a VTuber and not really show my face, but that is basically not possible because I am doing these scientific activities, and as part of my scientific activities, I would just, my face would be out there. So it's like, okay, yeah, it's fine. So if you guys, well, I guess I've never been against it anyways. It's more like just these traditionally VTubers don't show their face and I want to be quote unquote like my Oshi. So it's just why this. By the way, I do have long hair. As you see, I just hide it back. Yeah. Okay, anyways, yeah, let's actually get started. Yeah. Okay, so with the actual, so I'm just trying to, I think my drink is just not gonna cool down in time for me to start drinking it. So I should just not even try to start. Yeah, okay. So we are going to be rehearsing for this talk. End-to-end formalization of quantum error correction is the title here. This is a work with my I guess, colleague and also my advisor and his advisors. Yeah, and it is, I'm a grad student, so you guys probably know that part. Okay, anyways, yeah. So the overview, of course, we are going to start with our main contributions, and we are going to also be talking a little bit about the related work backgrounds as usual, especially because my target audience does not know much about formalization. So I would just, tell them about, well, this is something I have to talk about anyways. Yeah. And then I would be talking about what is interactive theorem proving, and talk about quantum error corrections as well. And then I will be actually talk about what do we do here. Yeah. Okay. So, okay, main result first, our contributions. So we formally verify the distance of quantum error correcting codes using the lean proof assistant. There is it's fine if you guys don't know what formally verify means here or what lean proof assistant is. That is what we are going to what I will try to tell you about today. Okay, so I need to fix the what is it called? The fact that this moves. That is what I mean by scuffed. But anyways, yeah. This includes the 72 qubit bivariate bicycle code, which is one of the quantum error correcting codes we care about. And maybe by the end of this talk, you will also see why this is a pretty big highlight of our project. Besides the fact that this is a lot of qubits, but also you will see, yeah. Maybe I would just say this is a little bit different from other formal verification proof of system projects. You will see why. Okay. So, but first of all, related works and backgrounds. Okay, so there are some other works that are also doing formal verification. When I say formal verification, I mean doing the interactive theorem proving. Again, I will say what it is later. But basically, other works that also do interactive theorem proving in quantum computations. So there's this square line of literature. I mean, this is also came from a lot of this came from University of Maryland. So I actually know a lot of the people in this line of literature. But they basically do like verify some quantum circuits, including Shor's algorithm for factorizing factorizing numbers. Uh, the usual story that I mean, I think all my target audience know it, and I think if you are still here by now, you probably also know what this is. But yeah, they verify some kind of open chasm thing, so it's actually runnable. Yeah, and then there's also this other line of literature that basically verifies quantum programs. I will maybe brush a little bit under the rock what's our difference between quantum circuits and programs. But basically, in programs, you can have like if-else statements, you can have loops, and basically you have like normal program constructs. While for quantum circuits, you are just looking at like matrices, right? So there's basically the differences between these two works. And then there's this other, I mean, okay, so both of these lines up here are more about, about programs and algorithms. And now this one is more like mathy, I guess, or more theoretical. Basically, there's this quantum info thing that basically verifies this lemma. I don't know too much about this lemma myself either, unfortunately, but this is just a related work. And funny enough, is we are part of this line, so maybe we should know this. I should know this a little bit more. But anyways, yeah. And then there's also this other related work that's actually concurrent to ours. They basically verify some other quantum error correcting code, including rotated surface code, toric code, and others. Um, yeah, I was thinking I should take time, but I think that's fine. I can just look into a VAR to know like how long I take. I am I'm hoping this is about like somewhere between 90 minutes to 2 hours long, because the actual talk slot I have is 2 hours. I know it's very long, crazy, right? Uh, yeah, usually talks are like 20 minutes long, but this is, I guess, part of why this is so scarce, because 2 hours is just so much. But I try, okay. But I guess the other things that is just a technical deep dive for people who have never worked with this before. So these backgrounds would hopefully, well, not like hopefully, but I would just say the plan is for this to take like 45 minutes or something. Yeah. Okay, so what is interactive theorem proving? Well, I guess one way to think about it is that it is just a different format. By the way, am I looking at camera? I feel like if I do this, then I would be looking a bit closer to camera, right? By the way, this is my phone over here. So I'm using this to monitor a YouTube chat. Not that I would be getting any, but it's just how I usually do, streaming a bit, streaming activities and all that. Yeah, anyways, back to being productive here and back to the rehearsal. So what is interactive theorem proving? Okay, so one way to think about it is basically that you have it's a different format to write your proofs. So for example, you could have LaTeX, of course, as usual, and then you write your LaTeX proof, it compiles into PDF. But then for interactive theorem proving, you can write your proof in a different format and it compiles to, well, HTML. That is basically how you usually do it. Just take a drink of this. Hmm. Sorry, need calories. Yeah, did not have dinner yet. I will after this, so it's fine. Yeah. Anyways, so what do you gain from using this format, right? Hmm. Oh, hmm, hot. Way too hot. Sorry. Okay. So they say if your LaTeX theme has a error, right? Then what is going to happen is that you compile into a PDF. That PDF would just have the same error because I mean, of course, the compiler is not smart enough. Maybe some of them have a spell checker or whatever, and it catches some typos. But these compilers don't understand math. So if you have a bug here, you have a bug here. But then this is what is neat about this interactive theorem proving is that basically it's the format that if you have anything wrong or if you just not necessarily wrong, but if your proof is just not convincing enough and the tool is not it's not convinced that you have a correct proof, then you just have an error, then you will not be able to compile it. So it's like a compiler checks for you. Okay, but I know that this sounds very vague. So next I will show you how this proof actually looks like and what this format actually looks like. It's best to do it through an example. So let's just do it for a simple lemma. So the lemma being that, well, for all, this is a simple number theory thing that for all number n, there is a prime such that the p is greater or equal to n. Is infinity of primes. There are infinitely many prime numbers. Okay, and the proof is I mean it is relatively simple, but let me also just read through it. So suppose for contradiction that every prime is less than n, then you define this very big number n factorial plus one, and then that p be a prime number that divides x. Then by assumption, because every prime is less than n, we have p is less than n. Sorry. And because p is less than n, we have p divides n factorial. And because p divides both this and that, then p divides one, and that's contradiction. So let's prove. Okay, so let's see what does the lin look what does the proof look like in lin. Well, I guess first look at what the theorem statement looks like in lin. So hopefully this part is human readable to people who are not lin programmers. No, just for all numbers n, there exists p such that p is prime and p is greater or equal to n. Hopefully you are convinced that this is a faithful encoding of the theorem statement, except the fact that I have a word theorem here and lemma here. Yeah. Maybe I should fix that. Let me take notes. Um, where do I take it notes? Oh, lemma versus. Oh, I fixed this already. Okay, theorem. Okay, sorry. Yeah, I promised scuff, right? So here you get scuff. Okay, good. So what was I going to say? Okay, so what is this? Well, okay, if you see check marks here, then that means it is proven. I will show you the HTML version as well on the web page, but for now, this is what we have. And then maybe I should also show you what is this. Well, first of all, this is my proof, as you can see, that I can change my proof. And if I change it in some ways, then it becomes not validated anymore. Okay, so now maybe I should also show you how to work with this tool, I guess. Okay, so right here on the right-hand side, this is link info view. Basically, you can read through your proof, and then it tells you what is proven and what is not proven yet. For example, if I have, x is n, n factorial plus one, and p is the number we have here, then it shows here on the link info view on what do we have defined so far and how far are we into a proof. Okay, So I mean, I'm not going to go like very, very deep into a proof, but basically let's just go through this just to provide some kind of intuition. Okay, so let's say my cursor is here. So I've stated a theorem and I haven't started the proof yet. Then the thing tells me my goal is this, which makes sense because the goal is for me to just prove what I've stated. Okay, and then now let's say suppose for a same contradiction that every prime is less than n. Basically I just this is how you write this in Lean. I'm not going to spend too much time on the syntax, but basically let's say if I at this point the hopefully this looks familiar. Basically, I want to say let suppose for second diction. So now I want to prove false. And now I'm assuming that for all prime for all p, if p is the prime, then p is less than n. So hopefully this reminds you of what was on the LaTeX earlier. So just take another drink. Hmm. Okay. So now we want to define these two quantities also as we had before. Then we have this here. Oh, by the way, min fact, maybe we can also just demo real quick. So let's say min fact, let's say 77, then this is 7, right? Because this is 7 times 11. And 143 would be 11. So because this 11 times 13. So this kind of works the way you expect. So now we also want to prove that the smallest factor of x is a prime. The smallest prime factor is a prime. And there we do have it. The proof seems a little bit tedious, and I'm just going to hand wave it and say that okay, now I've proven it, and now Lin has accepted that this is a prime. Okay. So now next we want to show that P divides n factorial. This is also some proof that I have to write down. And I have successfully convinced that P divides n factorial here. Yeah, okay. So now basically, well, where's our contradiction? We want to say that to reach false, it suffices to prove P divides 1. And then we prove P divides 1. And then that is kind of what the goal, what the thing looks like. Okay, so next we want to show the HTML version as promised. So yeah, I think it's in docs and then I think it's like docs, right? I'm pretty sure it is, yeah. Okay, so doc build and then leg build and then doc. And then I should be able to do this, yeah. It's smart enough to a sure, why not? Okay. So what do we have? I know I have this somewhere. Oh, it's just this, and then you find main primes. And you see the thing has come through. Oh, let me look at the source. Is it working? Oh, wow, it is. Because of course it will be. That's nice. Okay, good. Yeah, so where are we? A kill this off and then go back to the slides. Yeah, so this is how it works. Um, okay, so now let's keep going through the thing after I get slightly more calories. So this is too thick. I need to like add a little bit of water. Sorry, let me just get up and add some water to make this a little bit thinner, and then so I can take another sip. Hopefully, stir it a little bit more. Sorry, just the usual stuff. I mean, the thing is that if you guys are probably not here for the tag, right? So if you were, you probably click the link in the comment already. So so I'm sure you guys don't mind, right? You guys are just here for me, right? Or maybe you guys I don't know. I don't know. Yeah. mm. I feel I haven't been around as much. I mean, kind of makes sense, right? I've been on campus like 3 or 4 or 5 days a week. So it's just been long days. But yeah, we are going back to Rehearsing in a couple of days. Uh, yeah. Hmm. So just a little bit more before we get back to being productive. I promise we'll get back to being productive at some point. We just need to finish the this like powder-ish thing, like this thing at the bottom of my cup. Like this is really funny. Like this kind of like actually I don't know how to explain me that. Um, it's just some kind of drink that is like really thick, some kind of tea. Uh, that's made with this powder. But yeah. Anyways, why interactive improving? Let's go back to this. Yeah. Okay. So I mean, I don't know if how many of you have reviewed papers before. I know my target audience has, or they have at least read papers and probably found bugs. So yeah, and that is maybe a good motivation. Basically, let a well, because like this thing checks for bugs for you. So yeah. Uh, And I guess the incredible thing is that it doesn't check only for theory bugs, but it also checks for implementation. You can use basically the same tool chains to also kind of prove that your thing has no implementation bugs. And that is in fact what field cryptography project does. If you don't know this about this, by the way, I guess a lot of you guys don't. Uh, but this is basically at least a lot of my target audience don't. But this is basically a something that basically we use every day. Like I'm using it right now because I'm running Google Chrome, and this is part of Google Chrome. So yeah, um, and then this is also verified using the same like interactive improving thing. And the reason why you wanted this is because if you go into Appendix 1 and Appendix A, they have a list of a bugs that you've seen, like a list of implementation bugs. Like these are a how should I say? Well, maybe let me just click one of these exploitable bugs. Basically, you see ECC, so curve, elliptic curve cryptography, and then SSL server, and then you have a really terrible bug. You can recover entire private key. So this is really bad. Yeah. So basically, you have bugs, implementation bugs that you need to yeah, that this kind of tools also help you roll out or help you fix or help you prevent. Yeah. Okay, and the last reason is that, well, I mean, verification, it used to take like a lot of expertise because, well, who knows how to write this, right? A lot of syntax. And it used to be the case that it would take like at least a semester long class or whatever, but not anymore. Because right now there's this thing called byte coding, which basically means that just kind of, you know, just kind of hand an AI a PDF or a LaTeX and ask it to translate to Lin, and it does it for you. So yeah, try sometime. It is really nice. Okay, so actually, yeah, I mean, I don't want to go into like storytelling mode, but I feel like this is something I would this is a story that I've told my target audience already because I've been here on at Sinica for like a week, and I promise I will share with you guys at some point as well. Yeah, but this is really nice. Well, long story short, basically uh how should I? Why I might as well tell a story, right? Like this is like end of the day. I've been working hard all day. Let's like up just a little bit more. So basically, what happened is that I handed a AI a PDF. I think I did this part off stream, right? Or did I do it on stream? I forgot. I think I did this off stream, But basically, I handed the AI some kind of PDF, and then it some kind of LaTeX proof, and the AI says that it can do it better, like do a easier proof. I did not believe it, so I just asked the AI to give me a rock proof, a interactive theorem proving proof, like just proving interactive theorem prover, and it did it. So yeah. Hmm. Sorry, just a tea, because why not? Oh, actually, I can keep talking while here. Yes, good. Yeah. Anyway, so what was the next slide? The problem is I don't remember. Sorry, I'm just trying to. Okay, where are we? Yeah. Okay. Yeah. So properties of a interactive theorem proving, or just some facts, I guess. So interactive theorem proving is a type of formal verification. Formal verification is a very big umbrella term. Some of my target audience is working on some other type of formal verification, so I can probably just mention that on the actual talk. And then, well, how interactive theorem proving works is that at least behind the scenes, it is encoding mathematics with axioms and inference rules. Just like how you would do it in like actual mathematics, it basically just do the same thing just programmatically. Yeah. So, but maybe let me just quickly say what are these axioms and inference rules, because I was a math major, but I don't know how much of my target audience are. But yeah, basically, the I guess one fact is that as long as you have axioms and inference rules, you can like define pretty much everything under the sun. So, for example, if you have set theory, then you can get natural numbers out of set theory, and then you can get basically everything from there, because once you have natural numbers, you would be able to define a integers and rational numbers, and then you can start doing real analysis. So basically, the foundations of the entire mathematics can rest on just this. Uh, but you also need inference rules. Um, like for example, universal instantiation, as you guys, as some of you might have heard. Well, Socrates is, wait, how does it go again? All men are mortal. Socrates is a man. Therefore, Socrates is mortal. Yeah. So that is universal instantiation, and double negation in mention. You guys probably can guess what it is just by looking at this. Yeah. So this is kind of how what is going on, well, both in math textbooks and also what happens kind of behind the scenes in this like proof assistant softwares. Um, there's a small caveat. Basically, they're actually running this thing called Curry Howard. Basically, I mean I was just like kind of brush this under a rug, but basically the idea is that instead of having set theory, they usually have this kind of thing called type theory built in, which is stronger than set theory. So you have that, and then inference rules. On the inference rules side, they also have this like trick called proof terms, which is a I also don't know how to explain it very briefly, but there is this like I guess this proof term kind of like I guess I can say it's like they have structure kind of thing. Basically, it's a way to kind of manage proof and say that how do I describe it? Mm, by saying that okay, you have only so many inference rules, and each of these inference rules corresponds to one constructor. That is such a way of talking about it. Um, yeah, maybe I should just say there's this like this thing called proof term that helps you record the proofs uh based on like how these inference rules are applied. Yeah. Okay. So soundness of proof assistance, basically proof assistance. like Lean, like proof assistant is just a different it's just it's just how we call this kind of tools like proof checkers. They are designed to never accept wrong proofs, unless Lean itself has a bug, of course. But there are a few reasons why we are kind of confident that it probably does not have a bug. Yeah, or this is far less likely that Lean has a bug than whatever paper you're trying to verify. Yeah, because there's just a lot of Lean users, and if there were a bug, it would have been caught a long time ago. There's also some other like small kernel property or whatever that I would just sweep under a rock and just say that we kind of believe that this thing don't have a bugs. But on the other hand, there's this thing called incompleteness. Basically, you just cannot prove all true statements. There are going to be some true things that you just cannot prove. And that is not because you are bad at designing proof of systems or whatever, but there's like this Gödel's theorem that just shows that this is just impossible. Just like some stuff like hosting problems, something is not computable, stuff like that. It's just a hard limitation for any axiomatic systems, axiomatic and logic system, whatever. Yeah. Okay. And but on the other hand, it is basically good enough to encode any pen and paper proofs given polynomially many days, or I guess a given polynomially many tokens if you do by coding. Yeah. Okay. So I'm going to make some actual tea this time because I'm done with me there. And it would be nice to have some. I don't know if I want oolong or if I want the black tea. Um, maybe black tea. I've had enough. I had so much oolong earlier today. But yeah, where are we? We were talking about a oh yeah, QEC backgrounds. Sorry, I'm just waiting for this thing to boil. Or I guess you guys can consider this, and I can also try to see if I can talk about it without looking at the screen. So basically, why is text on the boil? Whatever, I will just come back here and go back there later. Okay, so basically, I mean, this is just kind of how error correcting code works. Basically you encrypt it, and then there's some kind of error that happens, and then you decrypt it, and you hopefully get the same outcome. Meaning this error is as if this error has never happened. So of course you cannot correct all errors because, for example, if this error just completely erases your data, then you are kind of out of luck. So basically, you kind of how should I say it? Define a correctable error set, and you say you can correct everything in the set. But then there's also a global error set. For example, like you can maybe correct like low weight Pauli errors, but then you cannot correct all the other higher weight errors. I probably want to move this into a for all here. Yeah. Anyways, so code distance. So code distance measures how well an error correcting code performs. Like how in terms of like how much errors it can correct and tolerate. So this is the actual math. Hopefully, I can convince you that this captures that intuitive notion. So this part is saying that okay. So this part is saying the error is not correctable, right? Because you have two different inputs, and then this just maps one code into the other, meaning this is just not correctable. So this is just hopeless. So distance is the smallest error that you cannot correct from, meaning you can correct anything. Well, not necessarily correct, but you can at least detect anything that's less than D. That is maybe the point of why we have code distance. There's also this theorem that says that, well, depending on what kind of situations you are in, but usually if you have the code distance d, then you can correct like d divide like d over 2 minus 1 errors or whatever. Basically, like you can, as long as it's like less than halfway in between two code words, then you will be able to correct it. Yeah. Okay, anyways. So let me also tell you a little bit about how these things are built because this is just how it is. Yeah. So let's start with this like what how to detect errors classically. So one I guess the most like basic notion is basically checksum, right? So let's say if I want to send you a 2-bit message, then I just add the XOR. I just append the XOR at the end of the message. Then of course I can just double check the checksum, right? So if any of this is wrong, then I'll be able to detect it. And then, but then for whatever reason, a for the quantum setting, we like the term parity checks a little bit more than checksum. So this is just kind of how we want to kind of reinterpret this picture by saying that a now we have this parity check uh what is it called constraint that valid code word must satisfy this. Yeah. Okay. So now maybe just to give one example of a real error correcting code, um, the classical repetition code, right? So, if you suspect that you have a error, then you just do the most maybe a little bit inefficient, but natural thing to do is, like if I cannot hear you clearly, or then I just, you know, I just say something a few times until you eventually hear it, right? So that is kind of how it goes. Okay, so but then it turns out that the parity check, like you can rephrase this in the in the language of parity checks by saying that okay, now you want to check that all three of these are the same. That's the same as first checking if the first two are the same, and then checking the next two checking the next two bits are the same. Yeah. Okay. And then it turns out that you can just encode this into a matrix. And then you want to say that if you have this matrix, it turns out this is also a full description of the code like this, and this contains the same amount of information because you can just say that the code is the exactly a set of strings that satisfy this. Okay, so that is why parity checks are important. So now let's talk about quantum. So one way to do this is to basically just kind of a is to basically just interpret this kind of bit flip error into of x. Do I not have it somewhere? Uh, oh, I had it earlier, but then maybe I should just say that. Or is this fine? Maybe this is fine. Yeah. For now, yeah. Okay. So we want to say that we want to use the property that the standard basis is you know a is the is eigenbasis for Z operators. So basically you want to say that a this check is the same as checking the measuring respect to the eigenbasis here. And similarly, this other check is the same as measuring respect to the eigen with the eigenbasis of this. Yeah, right? Because I mean, hopefully that is right. Yeah, I mean, every time you have a one, you just pick up a minus sign, right? So if you have even number of ones, then you have eigen value one, which is what you want. Yeah. Okay. So this is basically just a way to translate this. And then you want to say that, well, now you can define this code space. Again, this is just the quantum version of this by saying that, okay, now the valid code words are basically the code words that passes every single parity check. So with eigen value one for everything in this set. Okay, yeah. And this is basically just a how you define this, but that is uh maybe I just scrap this like this is yeah, maybe this is more trouble than it's worth. I don't know. I need to think about this a bit carefully later. Let me just make a note. Mm, okay, so now we want to. So now I guess the point is that this actually helps us address all X errors. So we are actually halfway there because as you guys probably know, that Pauli operators form basis. So if we can correct all X errors and all Z errors, then we can correct everything. So if this if this corrects all X errors, then we just have the other one. Then we just do the same thing here as before. Then the code space, we just define similarly as earlier. Basically, that we just define the code space as all the states where in eigenbasis, in the plus one eigenbasis of everything in here and also everything in here. Yeah, okay. And of course, we need to make sure that these two don't fight each other's. So, in other words, you want to make sure that this is because one of these gives you mx and the other one gives you nz, and you want to make sure that this is not like degenerate or not empty or whatever. It turns out I'm going to brush a little bit of the math under a rug and just say it suffices to have this. This is more important if you are trying to design new code. But then for our purpose, uh, like we are just all the codes we see today will have this property, and that is kind of the end of it. Yeah. Okay. So yeah. Okay. Now let's just talk about code distance for this CSS code, like in terms of this parity check matrices. So we have, it turns out distance is basically just the minimum of the uh, distance x and distance z, where you have either x attack or z attack. Sorry about the crypto language. X errors or z errors maybe is a better way of phrasing it. Okay. And X error is undetectable if you have this. And then it also says that, but then you want a undetectable error that actually does stuff to your code. So, for example, like, uh, remember that this is in the eigenspace. So if I hit the state with something in here, then it actually does nothing. So we want to basically write down an error that actually changes my code word, like a non-trivial error. So so distance is actually this part has not changed, but you want the error to be so. But the first part here is basically saying that okay, it maps one code to another code and does not map to a same code. Is maybe this is maybe how you should correspond this to what we had earlier. Yeah, like maps valid code to valid code, and doesn't map it doesn't just map all valid codes to itself. Yeah. Okay. So that is the background, the QVC background. Okay. So now next we want to. By the way, like this is supposed to be a 1.5 hours long. So I feel like I would be under, which is maybe fine-ish, honestly. Yeah. Like I've been around for. I mean, I feel like I've been like wasting. I've wasted pretty much like 20 minutes out of the last like 45. So I guess I could kind of expect myself to finish this in like 25 minutes or less than half an hour. And this is probably gonna be less than half an hour either, which is I guess both good and bad. Yeah. Okay. But anyways, the verification pipeline. Okay. So the goal is to formally verify the distance of binomial bicycle codes. But the challenge is that there is no pen and paper precision scribe. So the situation is maybe a little bit differently. It is maybe a little bit different from earlier, where we had the sorry, yeah, where we had the like infinitude of primes, where we have a nice PDF proof, and then we just kind of transcribe it into lane. So why not? Well, and why I guess also ties back to why this project is a little bit different from I guess a lot of from some other projects I've done before myself at least. Yeah. Okay. There's this thing called bicycle. Well, I mean, just say what these are or how these are built. So the first step of creating a BP code is basically you just generate many candidate CSS codes. So it's kind of brute force search, and then you first use heuristics to filter out some like terrible candidates. These heuristics are like I don't know, like leaf propagation. You guys can I mean I know about them. You guys can talk to me about them at some point. But this is not related to this specific talk. I mean that is what I would say on online. But for you guys, I mean, you guys watch this, chances are you guys have watched me build a build really propagation decoders as well. So there's that streaming of activities, right? Okay, so a yeah, and for the surviving candidates, you just compute the code distance using solvers. Because earlier, if you see that this is a integer programming problem, right? Because now you are like this optimization problem, because you are optimizing this objective function over this, 0, 1 vector. Yeah, and then up to some constraints. Yeah. So you have these optimization problems, and of course, the natural thing to do is to hit it with a solver. Okay, so but still, why solvers? Well, because code distance is NP hard and co-NP. NP hard, I will probably not tell you why it's NP hard, but it's just known. It's co-NP because, well, to prove that the okay, so proof the code distance is big is co-NP, because the proof the code distance is small is NP. The reason being, if you want to say the code distance is small, you just you just literally write down the attack. Then then that is your that's your short certificate. Uh, quote unquote attack. Write down the error that is not detectable, then that is your short certificate. So therefore, the thing is in co-NP, and if it's both NP hard and co-NP, then unless you then if you found a short certificate, then then you'll be rich. Well, maybe not that rich. You are not solving P equal to NP yet, but you'll be famous. Okay. Anyways, so because you have both this and that, there is no efficient proofs, or there might be no efficient proofs. We should not expect one at least. Continue with solver. Oh, this is the just part of my target audience. Um, but yeah, for integer programming, which I don't know very well myself, there's this Groby solver and probably a few more. And then, oh, I wanted to switch the next two slides. So maybe like switch these two bullet points. So maybe let me just start with this one. So Boolean satisfiability. Um, I think I wrote this down already that I wanted to switch them. So yeah, I did. Okay, good. So this is maybe what people know a little bit, like what at least my target audience, the theory part knows more, because well they've always heard about like things being like this being a bit complete. That's like textbook, quote unquote textbook material, and then they know like textbook stuff. But then this is basically just have to reduce everything down into booleans and do this like conjunctive normal form or whatever. So blow my nose. So sorry, yeah. To make things a little bit easier, you basically have this SMT thing. Um, uh, User friendliness. allowing like superset of stability, where you are also allow more building blocks. It is you guys will see very soon, but it allows you to like module theories like you can a yeah, maybe let me just hand wave this and just say this is a generation for this that is more useful in proof assistance. Okay, so solvers in ITP, I'm missing a bullet point above, so maybe let me just say in words. I will fix it. I will edit later as well. But basically, the idea for solver in ITP is that you basically will ask a solver for a proof, and then you do this proof translation to a like for example, let's just say Lin, then Lin as Cadical, or maybe as CVC5, let me just say CVC5 for example. So Lin would ask CVC5 for a proof, and then CVC5 gives a proof to Lin, and then internally kind of translate it into a form we can understand and check. Yeah, and that works because there are some standardized proof formats. I mean, this proof might not be sure proof. Chances are that I'm not because CoMP, like I said earlier. But there is a large proof that these solvers can, I mean, these ITP tools can either understand or they can just, or some of the I mean, there's always caveats like some proof assistants, just besides that they are not going to translate a proof, and they're just going to kind of trust their solvers kind of thing, and just accept without verifying uh, pros and cons. Anyways, yeah, that is maybe a missing first bullet point. And then I want to say that, well, there is no integer solver integration today. Maybe I should make it at least a little bit softer and just say, well, this plus lin does not exist. Okay, in Rock. Oh, I took out some slide earlier, but this is one of the popular tools for interactive theorem proving. EasyCrypt is another one. And then for Lin, there is a well, maybe I should, since it is here, I should just say that SMT with Rock is a thing. And for EasyCrypt, it has a bunch of SMT solvers, and Lin has both SMT solver and SAT solver. But the caveat is that these solvers are often treated as what we call hammer tactics, which is maybe a little bit different from how I describe we would from how we from the picture I gave earlier. So maybe let me also say a little bit about what are hammers. So hammers are basically like these situations where you are, how should I say? Basically, the point is that these proofs are sometimes a little bit tedious to write, and back then we also do not have LLMs to write for us. So because of that, then we kind of just use this solver and give it like I don't know, like maybe 30-second timeout and see if we get lucky and see if the solver can just kind of solve the thing. So we basically do it when we kind of believe there's a sure proof, but we're too lazy to actually write it out. Then we just hit it with a solver and hope the solver can do it in like less than half a minute or something, and we just put a very short timeout. And that's a little bit different from what we are going to from our project, where we are actually expecting very, very long and exponentially, like asymptotically exp time solver runs. But it's just what it is, yeah. But it turns out that we still, even with that caveat, the thing still scales well enough, and maybe it can scale further if we put in a bit more work. But anyways, yeah. So the one of the challenges is that something. I guess I'm also kind of just looking at the time because there's this place that closes at 11 p.m. So if I finish before like 10 something, 10:20, I think, people go there and grab quote unquote dinner, which is actually what is it called, a midnight snack place. But if not, it's whatever. It doesn't really matter. I just go to convenience store and eat something else. I'm sure we are fine. Yeah. Anyways, yeah. So we want to do this a what is it called, reduction from a from integer programming to this format that is accepted by SMT. As I was saying earlier, SMT is a superset and quite related to SAT. So this thing is going to look kind of like SAT. The result would be similar to SAT basically. Yeah. Okay. So now remember that we had this earlier. So now to prove that this is bigger than that, well, we just say that it is equivalent to saying that anything less than this does not exist, right? Okay, so yeah, maybe I should just say that say this, right? That a this part is copied, and I want to say that there does not exist. Maybe I should have written somewhere, but yeah, there does not exist X vector that satisfy all three of these. Is maybe what we want to prove. Yeah. Okay, so now we want to kind of translate this into Boolean formulas, or into like some kind of, let's just say Boolean formulas. Yeah. Okay. So this and this are easy because, well, this is actually just already a vector of Booleans. So this is actually just this. How do you encode this? There are a couple of different ways, but yeah, let me just say this you can encode. And this is also not hard to encode because then this is fixed. This is as long as you know the parity check matrix, then you can kind of unfold this into this because then the dot product becomes an XOR, right? So I mean the matrix vector multiplication just is just take a dot product between each row and the vector. So that is the dot product and dot product over base base two, not base two, module two in Z2 whatever. Yeah, a that dot product it just becomes an XOR. Yeah, when one of the input is null, I guess I could on the actual talk I could like write on the board or something. Yeah, or maybe it's already believable. Who knows? Yeah. So yeah, equal to zero means you pick up a nut here, and then you just kind of say that yeah, you know, uh, you just kind of select from here. You select the relevant entries and you XOR them together and you get the result, right? I mean, hopefully this is not too hard to imagine. Okay. And then now the other constraint is a little bit harder. So you want this, but this is exponentially sized. So you don't want to just enumerate this. Otherwise, you get a very, very, very big formula and you are set. Yeah. Okay. So instead, you want to use this property that this is equal to this. And then you want to say that so if you want something is not in there, then you kind of you unfold this by saying that okay, there is something that is that this is equal to this. So let me see if I can easily say why is this a case? If not, I will probably just with it. Okay. So if it were not in the row space, so if it were not in the Oh yeah, maybe that's not hard because if it were not in the component, that means that means it's got some component inside here. And if it's got some component inside, then of course you can do this because you just take the same component and this one. Yeah. Okay. So this is maybe this is the first step. And then turns out that if you have a subspace, you can take a kernel. I mean, you can take the span, and then this becomes that this is still very big. But then if you take the span, then by linearity, you can just just do this as at the basis level and say that if this were one, then the one must have come from one of the basis elements. So you have this. Yeah, And turns out this is enough because then this is just, you turn this into a or, and then dot product is again a, oh, you guys can see me, so I should not like touch my face or whatever. So, so like not used to doing face cam things. Yeah. Okay. So where are we? Yeah, where are we? Sorry, it's too much thought. Okay. So this becomes a Boolean disjunction. Yeah, so this turns into this, and this turns into this, and hopefully this makes sense. Again, like this is fixed, so this that's why this trick works. Yeah. Okay, so C5 demo. Hopefully you guys can, oh yeah, maybe I can just show this off. So the first a so this is of course generated using a Python script, but hopefully this is human readable. So you have 72 qubit BB code. So you have 72 Boolean variables, and then the first constraint being the being, maybe I can just show this. The first constraint being this, which is this, and then you can just, this is just these XORs together is false, okay? And then this, one way to do it, not saying it's a good way. In fact, there's the improved version because this is not such a nice way. But basically, you can say IT is just if then else. So you just cast this into 0, 1 integers, and then you say that you add all of this together is less than the distance. Yeah. So, and then finally, you have the last constraint, which is this huge OR. So this huge OR is here. And then you have this XORs here, which is just this XORs. Yeah. So hopefully you can kind of convince yourself it looks like this. And then you can just call CVC5. Let me see. Uh Takes a few seconds. If I remember correctly, it should take like at most a minute or something. But then maybe while this is running, I can tell you what is the improvement here. It turns out that instead of a having all of this, yeah, so it does take a few seconds. It turns out that instead of saying that all of this and then say that all of them must add up to 5, at most 5, you can just define the locations separately. So you have location 0, 1, 2, 3, 4, and you force them to be in order. And then you define this V0, V1, you define this not as a independent variables, but you say that this is true if one of the locations matches the index. Yeah, so this is kind of a different way of encoding this, right? Um, the rest is all the same, by the way. So this is kind of just one optimization. If we do this, then you see it's much faster. But I mean, still not ideal because if you did this, then it will take a lot longer. And that is maybe what we need for, what is it called? I mean, it is, the proof is very long, but anyways, we can just, see a difference. I mean, maybe this is not very informative because this is because this is such a small instance, but I think this works, right? Yeah, so you still have like a lot of, yeah. Okay, so where are we? Yeah. Okay, so this is kind of a CC5 demo that you can add one constraint to make it faster. In fact, Yifang's group has something that is even smart, more clever than this. So that runs in maybe like about like at least one order of magnitude faster. maybe I should not. Oh, their thing is shoot. Maybe I should not put this here. Because this is recorded. Yeah, maybe let me do this. Uh, might be not public work yet. Okay. Yeah, I will remember to fix it tomorrow for tomorrow, and I feel like nobody really watches this anyways. Or yeah, I feel like by the time anyone watches this, Yufan's thing will probably be out. I hope. Yeah. Anyways. Okay. So yes. A Yeah. Okay. So Lin demo. Basically the where am I? Oh, there. Yeah. Okay. So here is basically a similar thing, but done in Lane, assuming it doesn't lag. So one of the first optimization is that we did something like this, which looks incredibly ugly. There's also a way to write matrices. Maybe I will, or maybe or not even that. I could probably just show this off. Let me see if I can find a matrix. I can probably find a matrix to show you guys what are the differences here. Maybe just unitary. Polys, yeah. Polys. Okay, so this is maybe a more sensible way of writing matrices if I can find one. Where my poly IXYZ? Um, I should try to know this for tomorrow. Yes, the talk is tomorrow. It's scary. We are not ready yet. But still, like, where am I like a oh, except if I mouse over it, I still don't get a poly. I still don't get a matrix type. Where are my matrices? Like, actually. Anyways, the point is pretty much just you want to figure this out now because I feel like if I don't, I will just forget. So these are in basic. They are not in basic. They are lay in the quantum info skeleton, maybe. Um, oh yeah. But this is like not very good. Oh, matrix unitary. This is not. Um, what are the better way of saying matrix? Because I know we do have matrices like everywhere. I just don't know what are the best. Maybe here. Okay, let's see. Do we have matrix? Yeah, we do have. Okay, good. Yeah. So this is maybe the better way of the actual matrix type. Basically, you have n by n matrix over the ring of two elements. Is maybe a right way of doing matrix. But then it turns out if you did that, then this would be very, very big and they would not like it very much. Yeah. So you have to kind of have compact, make it compact. So that's optimization number one. And then the rest is basically, it does something similar here. Um, no, yeah, this is the location constraint from earlier. And then these are, sorry if this just looks a bit funny. And then yeah, do I want to let me think. How much do I? Oh, maybe yeah, maybe this is I should just say this is maybe still what we can understand by sight, so like by human eyes. So maybe I could at least explain this. So you see, there are stuff that looks like this, right? That V0 is true if any of this is zero, V1 is true if any of location is one, and so on. And this is exactly how this is. Basically, error I is true if only if one of them is true. This is the location constraint, and then the rest is basically, just a kind of a loop. Like this is recursion. Just a really ugly way of writing a. It's just how this language works. But anyways, yeah. So I just kind of encode all the constraints here, and then you see like if the so here's what I prove here, basically, that a for all. Oh, if I have things here, then this is a for all. So I want to say for all possible locations and for all possible error vectors, given this constraint. So this is in fact not free variables. This is dependent on this, and then this is uh like for all of uh, this cannot be all satisfied. That is what this is saying. And then basically the idea is I just simplify this all the way down. Then I get a very big Boolean formula. And then I hit it with the stack solver. And then this solved. So there are, I guess, the other optimization here besides the matrix to pivot, but also here I'm calling a set solver instead of SMT solver. Earlier in the project we tried SMT, it's not nearly as fast and it cannot scale to 72 qubits. So basically, the at some point in the project, we just had to do some optimizations, and we are just not a yeah, and chances were not even fully done yet. Yeah, okay. Um, Oh, maybe I can change the shout out instead of saying that it's not public work. Shout out to Yifang for a change shout out to Yifang a gave us a gave us a suggested a even more a even an even more optimized version. Maybe it's better, yeah. An even better version. Yeah, okay. And then I guess the other thing I want to talk about is the like what we call end-to-end formalization, because this is, well, I mean, this is not proving anything about the this is not a, I mean, this is showing that a, what is it called? Just getting into a step a Buddhist thing. But the actual statement that we are interested in is the is this. Let me see if I can find it. What I'm interested in is actually that the CSS code distance is at least 6. And we can also do print action, by the way, to see if there's any bad assumptions. These are all clean. These are all native design, BV design axioms. So these are not real axioms kind of thing. Like these are all like reasonable things to assume. So this is fine. Yeah. Okay, so the difference is that we want to actually talk about what's the CSS code, and we want to kind of, well, I guess fine. The one of the thing to that we have verified is the is this, is this reduction. We have basically proven in Lean, among other things, that the reduction we had earlier from integer programming to Boolean satisfiability, like this reduction is correct. We've also defined what code distance actually means in Lean, uh, by basically defining what qubits are, defining what a as you can see, we define what a what states are. I mean, we take some of it from the quantum info, but we define what states are, what publics are, and what QECs are, and then we define all of this, and then we have the yeah, and then we actually prove that the in the what we call end-to-end way, that the distance of the BP code is 72 and is 6 or above, is at least 6, instead of actually yeah, that is the theorem statement that we actually prove by connecting all the dots. Yeah, and I mean the rest is basically just like a mathematics, right? That hopefully I have convinced you earlier in the first, like, I don't know, in the preliminary section of the background section of the talk that is doable. Yeah, so maybe I can just say how it's done. Okay, so example, the n-qubit Pauli operators. So we define the these matrices as usual. So now we're just basically seeing what's being done here. Taking maybe one of the easier pieces of example, just to kind of show you guys how it is like. So we define this as usual. The intuition is that can we just define the NQB Pauli group as this? Well, that is what we do in quantum crypto because Pauli one-time pattern stuff. But it turns out that that is maybe not enough because you are missing a phase, and you cannot. This doesn't work either because this is still missing a phase. Like this are both real, but this is complex. Yeah. So the actual way to do it is to define this function. Um, Basically saying that okay, yeah, you have a phase, and then you have the single qubit Pauli. You can fold them into n qubit, and then you say the n-qubit Pauli group is you define this as the image of this function. That is maybe the one of the correct definitions that we found. And then we can see in link just to kind of show how these kind of things look like. So we have oh, wrong file, wrong thing. Actually save close this and save close this as well now. Yeah. Okay, so Pauli, Paulis, and then Pauli folding. We want to say that. Wait, what? Okay. Turns out that Matthias maybe have done some other cool things in the file as well, and I'm disoriented. Good. So we have. Oh, this is ugly looking, but where's fold? I have injection. What am I doing here? Fold Oxford. Yeah, I think this is a one. This is the correct thing. Yeah. So I have fold being let a yeah. This is retable notation, but basically I'm multiplying this set with this a connector of a of Pauli's. So this is kind of how this is encoded. So it looks a little bit ugly, more ugly than I originally expected when I plan to present this. Technical debt, of course. And then, okay, yeah, what is this? Fold is basically saying that I have this, but I also have proven that this is an injective function by basically, yeah, this is injectivity proof here. Okay. And then maybe this is, oh, maybe this is what I actually wanted to show, yeah. So I have factor Pauli as this, and then I want to say that, oh yeah, this is what I want to show, yeah. Maybe in the actual deal tomorrow I can just skip all of this and just say that okay, a vector Pauli is just this and this. This is just a way to write down a n Pauli's because a it's a tuple, right? Like this funny way of talking about, yeah, it's an indexing, right? Like for everything between for all numbers between 1 to n, or I guess 0 to n minus 1, you have a Pauli. So collecting all of this together, you have a tuple. So you have n tuple of Pauli and this. That is a factor version. And then you tag the image, a fold. Then that is because this universe is just all possible factor Paulis. So if you map all possible factor Paulis using this fold thing, then you have Pauli group. Okay, and then you want to show that the thing is a well, I mean, okay, fine, that's the definition here. Yeah, and then we've proven that this full function is injective. Well, why do we care? because then we can do unfolding, and then we can say polyweights are well defined. Because otherwise, if unfolding is not unique, then you know you have multiple unfolding, and now you suddenly cannot take a weight. Yeah. Okay. So that is what we do here. We have proven that a we've proven that this is bijective to this. There's a bijection. Um, by proving that this is injective, which we have proven somewhere up there. So this is injective, and then this basically just comes for free. Well, not for free, but this follows pretty much. Well, I don't want to say directly, but yeah. And then there is this n-qubit Pauli operators. I mean, there is this also proven some other property of this unfold function, like it respects this community diagram by saying that to take the tensor of two Paulis, then that is the same thing as well. You unfolding and you multiply this together, you append the list together. This is that we prove somewhere. Halimau, I think. How does it even look like? Let me collect this. Um, if I cannot find quickly, maybe that is for the, maybe it's not for the best, but it's just what it is. Wait, but for polymorph, is this literally just multiplying to poly like the usual product? It might be. Then in that case, where do I actually do it here? Because I do, yeah. Oh, I do. Okay, yeah. So factor cron is literally just a multiply this together and then append these two together. Casting append, what is this? I don't want to think about it too much. It's just append. Yeah, this is just really stupid way of appending two tuples together because technical debt. Yeah. Okay. And we want to say that a taking this to taking a connector of two Paulis is the same as you first unfold both of them. You do this and you fold them back together. So this is proven. Do I don't want to think. I don't want to talk about it. Okay, it's not much technical depth. Anyways, this is a thing. Yeah. Because we care, of course, right? Because yeah. Okay. I guess one big thing that we actually care is impact computation because we want to show that the error is detectable if if it anti-commutes with one of the parity checks. It's just a fact. So we want to say that this anti-commutes if either of them is I mean it commutes if either of them is identity or less than. And you want to also show that if this was single Pauli and if it's general Pauli, then you have this. And then this is also proven here. Basically, we just, I mean, kind of don't want to trace code, but this is, oh, it's here, yeah. So if this is identity or less identity, or if this, and then we want to show that this is correct by a cases thing. Uh, what's correctness? I know there's some correctness proof somewhere. Um, oh, was that basically what was? Um, oh, yeah, it is. Okay. So basically, I'm saying that if my thing claims to commute, then they actually commute. By saying you multiply them together, then against Tenko Dev, I don't know why we're not just doing Q dot, like Q star P or P star Q or something. But basically, then if my thing claims they commute, then they actually commute. if my thing claims that they don't commute, then you actually pick up minus sign here. Yeah. So this is kind of how it is. And then in the general case, you also have, you just kind of collect all of the results and take XOR as you would expect. And then I also prove a similar lemma here. I say I am in we because we're a team. Simply not blind. What's this? Anti-commute. Oh, maybe I should first show this. Yeah. So anti-commute is basically what is this? Oh, the base case is false. Because that is just how you do XORs. And then inductive case is you just you just kind of append one of these, and then so this is what is it called, recursive definition, which is fine. Yeah. Okay, so this is just a recursive way of stating this. And this is basically just naming this anti-commute instead. Yeah. And then we prove that this also works as expected, I think, somewhere. Yeah, this is correct by saying that, okay, if this anti-commuted, oh, terrible memories. Okay, yeah, whatever. Okay, what is this? Actually, what is this? I should know this. Or do I just look at this and say we have this? Yeah, fine. Okay, yeah. Given these two, which are not actual Paulis, we should just grab the actual Pauli version. It's probably somewhere below. Yeah. Uh oh, because of course this. Yeah. Okay. At least for the actual talk, I will be able to find faster. But basically, the what we have is that if they anti-commute, then they actually anti-commute. That's proven. If my thing proves they don't anti-commute, so they do commute, then they do commute. Yeah. So this is basically what I've proven. So, anyways, there's a lot of like stuff that is a somewhere along that's been like proven somewhere along the line that I'll be more than happy to trace code. Just not now because I want to eat. Leave a comment or something, or I don't know, like a show up in my stream one of these days, ask questions. I will answer, I promise. um, yeah. Anyways, main theorem. Main theorem being this CSS is actually also defined somewhere. I mean, we define BB code as well by using the actual definition of this like a cyclic whatever. That's why it's called bicycle because there are two cyclic permutations. It's actually defined somewhere. There's this somewhere up there. And then to BSM, this binary symplectic representation, roughly speaking, that is basically a way to say that you can represent Paulis as a it's basically a way to formalize this by saying that for each Pauli you have a you can kind of say you have X and Z, like you can have X string and X and Z string uh in the face and you kind of brush the face under a rock. So that's what BSM means. Yeah. And then and now if you have BSM you have distance, and then this is all defined in the similar this distance is defined in the way I was saying earlier, that a yeah, I mean there's this BSM layer, there's a lot of a proof script that we had to write. Yeah. So there's that. Anyways, this is the main theorem statement, and then gives you list that you can check if you have any like assumptions. And turns out all the assumptions come from native decide, which you can drop. Native decide is basically just saying we call a C++ optimized subroutine, and we go out of the lane sometimes to do stuff for efficiency. And this decide is also just more native stuff. There's I don't know if there's a way to remove this. There might not be. In fact, I'm curious. Why do we have this? Let me see. So you have a What is this? Chris, no, dist X. Oh yeah, so for the actual thing, you also have this. But then for the other thing, I'm just gonna brush this under the rug and go it. Okay, so this is what we have, yeah, and this is what we've proven. That is maybe what I should say. And then to a what is it called? To audit the firm, you basically just kind of look at these axioms and see if there's anything you see that does not look good. Otherwise, you kind of are having this. And all of this I can claim are come from the standard library. So this is good, yeah. Okay, so thank you all very much. I'll eat and I'll fix this. Yeah. And I will be back for gaming in a couple of days because I have a 2-day meeting for this project as well. Long story. I hope I don't lose my voice tomorrow. My oh shit, yeah. Anyways, yeah. Uh, yes. Yeah, I will see you guys in a long day. Yeah. Thank you. See you. Well, how do I?